Fundamental identities. So it talks about the fact that we have conditional equations. These are algebraic equations that we have been given over time. They give the example of like 5x plus 3 equals 13. And you find the solution, which is a true statement. And then you can get a false equation where there's like a no solution equation. When you have something like an identity, this is true for all values in the domain, okay? So when you have something called an identity, this will always work for anything that fits the domain requirements. So if you look at these, the first set should be your easiest ones, okay? You should recognize these already from your right angle trigonometry, okay? So we have reciprocal identities. That means if I have the sine, the reciprocal identity of sine is cosecant. Vice versa, if I have cosecant, the reciprocal identity is sine. Meaning I can take one of those and flip it and get the other, all right? And so all of these should be very familiar. Sine corresponds to cosecant, cosine corresponds to secant, and tangent corresponds to cotangent. The second set of identities is called the quotient identities. The quotient identities just say tangent and cotangent are made up of quotients. Tangent is your sine over cosine. Cotangent is your cosine over sine. And so you'll see that all of these identities are really made up of sine and cosine. Because if I need tangent, I can actually use sine and cosine. If I need cotangent, I can use cosine and sine. So they're all really encompassed in the two basic sine and cosine functions, all right? The next set that we're going to look at are called the Pythagorean identities. Pythagorean should bring an explicit formula into your head. A squared plus b squared equals c squared. And that's what these identities are based off of. It is called the unit circle because your radius is 1 unit, okay? So 1 unit is why we call it the unit circle. And so if I were to draw a right triangle on my unit circle, the distance that I go right or left is my cosine value because that's my x value. The distance that I go up or down is my sine value because that's my y value. And so if I take one side and the other side, then I can set up a Pythagorean identity. I can say, well, sine squared, or a squared, plus cosine squared, or b squared, is going to equal my hypotenuse squared. Well, my hypotenuse on a unit circle is 1, so 1 squared is 1. This is where we get our Pythagorean identity, our basic Pythagorean identity of sine squared plus cosine squared equals 1. You will either memorize this or you won't make it through this section, right? This is your fundamental identity that you will hear over and over and over. This actually rolls into calculus as well. Sine squared plus cosine squared always equals 1. It doesn't matter what angle you have. It doesn't matter how large your triangle is. If you take your sine and your cosine, you square them and add them up, they will equal 1, always. Which means if you have one of them, you can solve for the other because you're only missing one variable in this equation, all right? From that, we get the other two Pythagorean identities. They are actually based off of this guy. The second one that you're going to notice is 1 plus tangent squared equals secant squared. And then 1 plus cotangent squared equals cosecant squared. So secant and cotangent go together, cosecant and cotangent go together in these Pythagorean identities. This is where they come up with this. You take your sine squared and your cosine squared equals 1 and divide everything by sine squared. Well, sine squared divided by sine squared is 1. Cosine squared over sine squared is cotangent squared, because cosine over sine is cotangent. And 1 over sine squared, well, the reciprocal of sine squared is cosecant squared. So from this identity, we get your 1 plus cotangent squared equals cosecant squared. And then from this identity, we get the other one. If you divide everything by cosine, you'll see that sine over cosine, that's tangent squared. Anything over itself is 1. The reciprocal of cosecant squared is secant squared. All right? And so from that 1, we get those 3 Pythagorean identities. Using identities to evaluate other trig functions. So we have seen things like this in other places. We've seen it with right angle trigonometry, that you can use right angle trigonometry to do this. You can also use all of these identities and work around it. So it says if the cosecant is 4/3 and the cosine is less than 0, that's the same thing as saying the cosine is negative, find the other 5 trig functions. So just like we did in the past, the first thing I typically do here is I figure out what quadrant I'm in. All right, that's the first thing I do, because the quadrant is going to tell me my positive and negatives for all of my other functions, right? And so for this one, it's telling me the cosecant. Well, that's the reciprocal of sine, all right? And they've told me my sine is positive, correct? And so there are only 2 places where my sine is positive. My sine is my y value. It is positive in the first and in the second quadrant, right? Make sense? So I've narrowed it down to 2 quadrants, yes? And then it's telling me my cosine is negative. So the only one of these where my x value is negative is this quadrant. So I am in the second quadrant, all right? It wants me to find the other trig functions, and specifically it wants me to use the identities. So when I find the other trig functions, what I typically do is I write them down to make sure I haven't forgotten any, and I usually write them down in order. So I'm going to say, well, I need to find the sine of theta, I need to find the cosine of theta, I need to find the tangent of theta, and of course my reciprocal functions. And I write them beside each other so I can see if I have an easy one to solve. I'm going to write down the one they gave me. They gave me cosecant. Well, cosecant is 4/3. Well, I have a reciprocal identity that will help me find one of these. A reciprocal identity will immediately give me what my sine value is, right? If my cosecant is 4/3, my sine then must be 3/4, right? And so I can automatically fill him in. From here, you can do it a multitude of ways. I have a sine. I can use my initial Pythagorean identity, sine squared plus cosine squared equals 1. I have a cosecant, so I can use my cosecant squared and my cotangent squared if I want to. It doesn't matter. But once I find sine and cosine, I have all of them, because I can use my reciprocal and my quotient identities at this point. So I typically go straight to my sine squared plus cosine squared equals 1. So I'm going to say 3/4, that's my sine squared, plus my cosine squared equals 1. And I'm going to solve this way. So if I square 3/4, I get 9/16, right? My next step is to subtract and then square root, right? So subtract this guy. My common denominator, if it's a 1, is always just my denominator, right? So I have that. What is 16 minus 9? So I'm going to get this 7/16. That is cosine squared, right? So I have to take the square root. The square root of 7 is not perfect, right? So we're going to leave it as the square root of 7. The square root of 16 is a perfect root. It is 4. However, which quadrant am I in? Well, I determined at the very beginning I was in the second quadrant. So what do I know about my cosine? It is going to be negative. So I have now found my cosine. It is negative square root of 7/4, which means I also know my secant, do I not? If I know my cosine, I know my secant. I can flip it. So it's going to be -4 over the square root of 7. What do you think I want to do with that? Rationalize it. So -4 square root of 7/7. I have found my secant. And once I have my sine and cosine, I have my tangent and my cotangent. I can use my quotient identities here. Tangent is just going to be sine over cosine. All right? By the way, anytime you have a fraction over a fraction and they have the same denominator, you're going to end up with numerator over numerator. Because when you keep change flip, those denominators will cancel each other out. So my tangent is going to be 3 over the negative square root of 7. I want to rationalize him, right? So he's going to be -3 square root of 7/7. And by the way, when I have this, if I want to flip it, I actually flip it before I rationalize it, because if not, I'll have to rationalize again. So instead of flipping him, I'm going to flip the one I didn't rationalize yet. I'm going to flip him to find cotangent, because that is going to be negative square root of 7/3. All right? So once you have sine or cosine, you have all of them. If they had given me something like cosecant and they just asked for cotangent. So let's say they said, here's the cosecant, give me the cotangent. I wouldn't go through the process of finding sine and cosine. I would go straight to my Pythagorean identity that deals with cotangent and cosecant, right? So if they give you one and just ask for a specific one, use the path of least resistance, all right? But if you can't remember that, then you can go back to the other ones that you know. Once you have sine and cosine, you have all 6 functions because of these identities. All right, the next one we're going to get to is co-function identities. This is kind of interesting to think about, but sine and cosine are always really 90 degrees apart, if you think about it that way. So this pi over 2 represents a quarter. And so if you were to take like an angle and drop it a quarter, you would see that they move. And that's how if you look at around your unit circle, you'll see that they kind of flip-flop places is what they do all the way around the circle, right? And so you have this little thing that happens when you are taking a 90-degree angle and subtracting whatever angle you're talking about. Why does this work? Well, think about right angle trigonometry. You have one that is a right angle. Your sine and cosine are always complementary angles, right? Because really, you have 2 left over that add up to 90. So all I'm doing is I'm taking my 90 degrees and I'm subtracting to get to the other guy. So if I have a 30, 60, 90, obviously in a right triangle, one's 90. The other 2 are always going to be complementary. They're always going to add up to 90 degrees. And so that's why you have this little thing happen with your trig functions, because all you're doing is saying, oh, well, if I have the sine of this guy, I have the cosine of the complement, right? And so that's what happens with these. You have the sine of one, so then you have the cosine of the complement of him. And that's all pi over 2 is. Pi over 2 is just 90 degrees. And so you'll notice that if you have the sine, you can either do the sine of theta or the cosine of pi over 2 minus theta. Tangent corresponds to cotangent. Secant corresponds to cosecant. These just flip-flop, right? So if you have one, you have the other. Sometimes when you're in an equation and you get to some point and you're like, oh, I could just do sine here instead of cosine because I have pi over 2 minus that guy. And so there are times when you can substitute in and substitute out to get these. They typically do this when they just want you to solve one way or the other, and you're going to see that example in just a minute. But these are called co-function identities because they are literally just complements of each other. And you'll always notice it in a right triangle. You tend to forget that when you move to unit circle, it's just right triangle in the coordinate plane is all you're doing. The next one that we're going to talk about is even and odd functions. These are kind of indicative of what happens when you look at where sine is positive, where cosine is positive, where all that happens. If you are taking the sine of a negative angle, you can just negate the sine. So for example, if I have pi over 4, the sign of pi over 4 is square root of 2 over 2, right? If I want the sign of negative pi over 4, I can just take the sign of pi over 4 and negate it. And that's all this is saying. You will notice that sine, cosecant, of course, they're reciprocals of each other, do that. So a positive or a negative angle is going to give you the same answer, just negated, okay? But with cosine and secant, it doesn't. Why is that? Well, if I do the positive angle, positive cosine of pi over 4, well, that's square root of 2 over 2. Cosine of negative pi over 4, I'm in the fourth quadrant. That's still positive for cosine. That's still positive square root of 2 over 2. So you'll notice that cosine and secant do not negate. The cosine of an angle and the cosine of that negative angle are going to be the same answer. All right? So those do not negate each other. But tangent and cotangent do. Why? Well, because one negates and one doesn't. And you have a positive over a negative, right? And so tangent and cotangent also negate when you negate the angle. These are called even and odd functions. And it stems from, remember way back in pre-cal when we talked about whether they were symmetric to the origin. Remember that? And symmetric to the x-axis and symmetric to the y-axis. And they were actually called even and odd functions based on their symmetry. That's where we get this from, that term there. The last identity on this part of it that we're going to look at is periodic identities. I just want you to pay attention to the fact that sine rotates, and we saw this when we did our graphs, every complete circle. So you'll notice that sine and cosine rotate every complete circle, secant and cosecant every complete circle, but you'll notice that tangent and cotangent they repeat every half a circle. All right, and so that's all this is saying. So sometimes they will want you to solve an equation over the entire 2 pi, and you're going to see it duplicate multiple times, or you're going to see it just duplicate once, all right, depending on what type of function you have. And it just depends on how many times it wants you to look at it, usually from 0 to 2 pi. This will come into hand when we actually solve equations, all right? So let's look at this. This is using cofunction and even and odd functions. So it says if the cotangent equals 2.25, find the tangent of theta minus pi over 2. Now, remember, my cofunction identities have pi over 2 minus the angle, not the angle minus pi over 2, okay? So if I want to use cofunction, it needs to be in that order. It needs to be pi over 2 minus my theta. So I can actually change this into that. I can say, well, this is the same thing as saying the tangent of a negative pi over 2 minus theta. All I did was pull out a negative, right? So far, so good. And we know that with tangent, for my even and odd, if the tangent of a regular angle is the same as the tangent of the negative angle, I just negate the whole thing. So for tangents, I can actually pull this whole negative out here, and I can say, well, that's the same thing as the negative tangent of this positive angle. Now, this is a cofunction identity. What corresponds to my cotangent when I take pi over 2 tangent when I take my pi over 2 and subtract it is cotangent, right? And so if you look at your cofunction identities, I can actually replace this guy with just the cotangent of my theta. And of course, I need to bring that negative down, right? They gave me cotangent, didn't they? What did they say cotangent was? Well, they said it was this guy. So I can replace cotangent with 2.25 and then just bring that negative down. Right? So all I did was finagle my tangent so that it looks like my cofunction and my even and odd identities. I rewrote it, pulling out a negative. I said, well, the tangent of a negative angle is the same thing as the negative tangent of that angle. My cofunction identity told me I could replace that tangent subtraction piece with just cotangent, and they already told me what cotangent was. So this first method of simplifying these trig statements, I guess, they're not really equations, is to just rewrite everything in sine and cosine. Like that's the first method. Now it's not always the easiest. We're going to do some where I would say don't do it. It makes your life harder. But your first method and your primary method is, would it be easier just to write everything as sine and cosine? And so if that's the case, then we're going to start there. And so this method is what most people just go to automatically because everything can be written as a sine or a cosine. And so I'm going to take each piece of this. Tangent. Well, I would rewrite that if I was using sine and cosine as sine over cosine. Tangent is sine over cosine. All right. Secant. Well, secant is the reciprocal of which one? Cosine. Cosecant is the reciprocal of sine, right? So now I have these two fractions. I have sine over cosine, and I have 1 over, and I'm just gonna write sine cosine. I guess it doesn't really matter, but we have something like this, cosine sine, right? It's just multiplication of fractions, just multiply your denominators, right? Now, if I were just adding or subtracting fractions, what would I tell you need to do? You need to find a common denominator. I have cosine and I have cosine sine. What's my common denominator? Just cosine sine. So my next step is to say, well, I need to figure out my common denominator. My common denominator is cosine sine, all right? Now this guy already has the common denominator, so he is not going to change, right? My first guy does not have the common denominator. What do I need to multiply to get that common denominator? So I'm going to multiply the top and the bottom by that. What is sine times sine? Sine squared. Now here's the thing. Anytime you see a sine squared and a 1, you should think, this looks like I can do something with Pythagorean identities. Now, sine squared minus 1 is not technically a Pythagorean identity, and they do this a different way. So they actually replace their sine squared with something. But I will say you can manipulate your sine squareds plus cosine squareds equals 1. So if I'm gonna write this guy out to the side. Sine squared plus cosine squared equals 1. I want sine squared minus 1. So I'm going to make this guy look like sine squared minus 1 equals something, okay? So that means I need to move my cosine squared to this side, right? And I need to move my 1 to that side. Does everybody see that? I can rewrite it. I can say, well, sine squared minus 1 equals negative cosine squared. Everybody see that? I moved my cosine squared to the right. I moved my 1 to the left. The rule of substitution works here. I have sine squared minus 1 in my problem here. I'm going to replace it with what it equals. So I'm going to replace that whole numerator with negative cosine squared theta over my cosine sine. So far, so good? Can I simplify this even more? Yes, it's like having an x squared over an x. What can I do? I can reduce it. I can reduce it by 1 cosine on top and bottom, right? So now on top, I have negative cosine of theta over sine of theta. Can I simplify that? What is cosine over sine? It's cotangent. So negative cosine over sine equals negative cotangent of theta. And that is simplified. like I said, certain things should make you think of something. Pi over 2 minus x should make you think of an identity, right? That should make you think of a cofunction identity, all right? And so if I see sine of pi over 2 minus x, clearly that is not the easiest way to manipulate this. Getting rid of that pi over 2 over minus x is obviously what I want to do first. And so my cofunction identity here tells me that I can actually replace this whole thing with what? Cosine. So I can say that's just times the cosine of x. All right. Now, here's the thing. You can combine those, cosine cubed. You don't have to. You should see something in common between these that I can factor out. What can I factor out of both of those? A cosine. I can take a cosine out here and a cosine out here. So I have cosine of x times cosine squared x plus sine squared of x, which should also just blatantly ring a bell. What can I replace cosine squared plus sine squared with? They always add up to 1. 1 times the cosine of x. What is anything times 1? It is itself. We'll go ahead to the next one. All right. Simplifying by combining fractions. All right. So when I have this, there's actually a couple ways that people start to do these. But when you have something like this, you want to think, well, I do need a common denominator, right? And so while it's not a pretty common denominator, if they don't have anything in common, you just multiply them. And so my common denominator here is actually going to be sine times 1 minus cosine of theta, right? That is my common denominator. And then I multiply the left guy by the 1 minus the cosine. And I multiply the right guy by just the sine. Right? So far, so good. So even though it's not a pretty common denominator, it is my common denominator. When I have... and I'll show you this for just, so when I have something like this, the only thing you're going to do at this point is you're going to start simplifying, all right? I'm not going to simplify the denominator yet. I'm going to just distribute this cosine. So I end up with cosine of theta minus cosine squared of theta minus sine squared of theta, which again should make you think of something, right? Now, for Pythagorean identity, those do have to be added. But you can take out a negative, right? So if I were to factor out this negative, so let's say I could do it this way, minus, and I'm going to pull a negative out of these, I end up with cosine squared plus sine squared. Everybody see that? And I have that over sine of theta 1 minus cosine of theta. Yes? All right. Cosine squared plus sine squared, again, what can I do with that? This is just going to be a 1. So I end up with cosine of theta minus 1 over sine of theta 1 minus cosine of theta. This should ring a bell from when we've done simplifying before. Anytime you have the same two terms and they're flipped, you can do what with it? What can you pull out of one of them? and make it look just like the other. So up here, I have a positive cosine and a negative 1. Down here, I have a positive 1 and a negative cosine. So I can actually take a negative out of this numerator. So I can rewrite this numerator as a negative 1 times 1 minus the cosine of theta. Anytime they're just flip-flopped, you can take a negative 1 out, right? And so now you should be able to see that I can cancel those, right? So I can cancel this guy with this guy. On the top, I just have a negative 1. On the bottom, I have sine of theta. Hopefully, you know you can simplify him. What's the reciprocal of sine? It would be cosecant, and because of that negative 1, I have negative cosecant then of theta. So this whole guy simplifies to him. All right. So this is a single term. It's not like I'm getting common denominators here. It just wants me to write it without fractions. And so this is something people don't typically think of. But the only thing that's going to help me with a 1 and a sine is if they were squared, right? And so you can actually multiply by the conjugate here. All right? So think about when you were trying to rationalize a denominator that had a square root plus something or whatever, or when you were trying to rationalize when you had an I in your denominator, right? You were dividing with complex numbers. You can multiply the top and the bottom here by your conjugate. By conjugate, it's just changing the middle sign, right? Instead of 1 minus sine x, I'm going to multiply the top and bottom by 1 plus sine x. Now, hopefully your fraction knowledge knows that anytime you multiply the top and the bottom by the same thing, you haven't changed the fraction, because top and bottom is 1, right? X over x is 1, okay? So I can multiply the top and bottom of this fraction, and I haven't actually changed it. So on the top, I have 1 plus the sine of x. And on the bottom, anytime you multiply conjugates, you get 1, the first one squared, minus the second one squared. All right? This should look like a Pythagorean identity. Remember I said that you can manipulate your Pythagorean identities, right? I want 1 minus sine squared. I'm just going to move that over. Cosine squared equals 1 minus sine squared. Right? So I can now replace my denominator with cosine squared. 1 plus sine of x over cosine squared of x. It wants me to have no fractions. So when I have a numerator that is adding and subtracting and one common denominator, just like I can combine fractions that have a common denominator, I can separate fractions that have a common denominator. So I can separate this into 1 over cosine squared of x plus sine of x over cosine squared of x. All right? It wants me to have no fractions. I can definitely get this guy as no fraction. What's the reciprocal of cosine? So I can write this as secant squared. What about this guy? Well, I could say sine over cosine times 1 over cosine, can't I? Is that sine over cosine squared? What's sine over cosine? Tangent of x. What's 1 over cosine? It's secant of x. So I rewrote this guy as an expression with no fractions. With no fractions.